All right, so we've been making progress on automating the exploratory data analysis process. And in the prior videos, we've gone through how to automate univariate statistics, then how to automate bivariate statistics, and we finished the bare bones minimum for a good exploratory data analysis. However, there are a few things we can do to improve it, and in this video I want to focus on one of those. In particular, when we're analyzing numeric to numeric relationships, it's common for us to have features that don't meet all of the assumptions of a linear regression, which is one of the common algorithms we might use later in the modeling phases. So in addition to calculating a Pearson correlation, which again assumes a linear relationship, there are a couple of other correlation metrics we might want to also calculate, and we can automate that process too. In particular, I want to add Kendall's tau here for nonlinear relationships or non-normal relationships, and then also the Spearman's correlation for rank ordered discrete relationships. So let's go ahead and head back to our code here, and we ended off with, let's see, right here. We had pulled in 3 datasets to use as examples. Again, links to those in the description. We had taken a function we created and processed different statistics depending on the data types of the 2 features in the bivariate relationship that we're analyzing. And then we were printing out a table of all these calculations. So here we have the p-value. No matter what type of relationship it is, we can get a p-value, and so I rank ordered it based on that. Then we had the Pearson correlation here and the linear regression equation. And then if it was a categorical to numeric feature, so for example, smoker, and we're analyzing that against insurance charges, instead of doing a correlation, we calculated a one-way ANOVA. But of course, that also has a p-value. And it printed out in this table. So what I want to do is, and then I forgot to mention, we also modified that by adding functions that would create visualizations in the format we liked that would then automatically be combined, here we go, into one big bivariate function that not only calculated our statistics, but also called those individual visualization functions within each one of these process flows. So the result is, when we run the bivariate function, let me go ahead and pull in the datasets. Back up top here. Got to mount Google Drive, of course. Read those in. There we go. Right here. This bivariate function, we run that. It does both. Oh, we got to run the cell before it to store it in memory. It gives us both the individual. And I got to run all of my individual visualization functions again. You might remember in the first video, we'll put these in a separate file here when we're all done with this. There we go. Now we should be fine. All right. So it automatically creates both the visualizations for each bivariate relationship with the relevant statistics, and then finally prints out that table for us at the very end that includes the summary of just all the relationships. So I want to modify that function to include not only the Pearson correlation, but also the Kendall and Spearman correlations, and maybe some useful information, like we added missing data so that we could be aware whenever we had to drop rows in order to calculate these scores in a prior video. Let's also add relevant metrics in this table that help us understand when we should use the Kendall, Spearman, or Pearson correlation. All right, so to do this, I'm going to go back up to my last version of this overall function, and then I'm going to copy in some extra characters here. So let's put the additional correlations here after the R. I'm going to make one for tau, one for the Spearman, and I just went to Google to copy these characters. So here's the tau character, and the, I don't know what's called, PHO, I forget. You can make fun of me for not remembering that. Anyway, this is the Kendall, this is the Spearman. So we've got a place for both of those. For the Kendall, the criteria is we prefer the Kendall correlation over Pearson if it doesn't meet the assumptions of linearity or the assumption of a normal distribution. A quick way to analyze whether I should use a Pearson then or Kendall is just to add skewness to the table. So maybe up here next to missing data, I'm going to add a column for skewness. So whoever's reading the data can look at that score and then decide whether they want to use R or tau here. And you might decide that you'd prefer just to calculate skewness and then only show one or the other. You could call the column just correlation and only show the one that you think is most relevant. But I'll leave that up to you. I'm just going to go ahead and calculate both, actually all three here, and then let the user decide. The next question, though, is how do I determine between the Spearman correlation versus one of these others? Let's say that it is normally distributed or that skewness is acceptable. How would I determine whether I should use this one? Well, there's a couple criteria we could use. First would be, is the feature discrete? So Spearman is for rank-ordered data. Rank-ordered would mean that it's a whole number, like 1, 2, 3, 4, 5. However, just because it's a discrete number, that doesn't necessarily mean that it's rank-ordered. For example, a column like children here in the insurance charges, children is discrete, but it's not rank-ordered. So a rank order would be a situation where the difference between number 1 and number 2 is mathematically the same as number 2 and number 3. However, meaningfully, it's different. For example, the results of an election. If you finished first compared to someone else who finished second, you might have finished first by a single vote, whereas the person who finished third was third by thousands of votes. So that even though their rank order implies that they're only one digit different between each of them, there is a much bigger, more meaningful difference than that, and it's different for every rank. And so I would need a couple things. I would need to know first whether or not the feature is discrete, and then also maybe how many unique values there are. That could help, because if it was something like age, maybe there's 100 unique values, and that's, even though it's discrete, that's a pretty smooth distribution, or it could be. Whereas something rank ordered might have fewer options, like a variety of examples. So I think the two things I want to include to help us make that decision here is, first of all, the data type, because that will tell us if it's an integer or a float, so we can determine what we want there. So I'm going to call this type for the data type of the feature. And then I'm also going to include unique for the number of unique values. Now, I know we included all four of these things in our univariate table. So I'm not saying that we shouldn't include them there. I'm just saying that in this bivariate table, I would go ahead and include them again, just because it helps me understand which of these correlation measures I should use when I'm analyzing the bivariate table. So let's go ahead and add each of these things. They all apply. Type and unique, these two apply whether it's a numeric or categorical feature, where skew only applies to numerics. So let's put everything in the proper place. So right here is where we calculate stats that apply to all data types, because this is in the for loop as we're going through each column one at a time. We've made sure that we're not dealing with the label, and it's before we get into the data type block. So missing data, like we did before, is one example of something we'd calculate that applies to all data types. Let's just add some for D type, and I'm going to call that one, let's see, df temp. I'm going to use the one where we dropped empty records and created right here. So df temp feature dot D type, and then let's do one for unique equals df temp feature dot n unique. And then I can add those in. I'm going to wait and put them in here when I insert a row into the data frame in just a moment. Next, though, I want to take care of skewness, since I have it right here. And I only want to calculate skewness if the feature is numeric. So that's going to happen potentially in a couple spots. So here is where I'm looking for end-to-end relationships. I'll definitely want it there. So before, I better calculate it before I need to insert it here into the data frame row. So I'll put it here after I calculate the linear regression equation, and I'll say skew equals feature.skew. And then I will potentially also need it down here in a C to N relationship if it's the feature that is numeric. If the label's numeric, I'm not going to worry about it. But however, well, I guess you could argue, I'm getting kind of off track here. A C to N or N to C relationship, we're not going to calculate a correlation measure for that. However, for a t-test or ANOVA, there is some assumption here that the numeric feature has acceptable skewness. Do I want to go ahead and calculate it there anyway? It's not quite as critical, but it's still important. Yeah, may as well. Not a big deal to add it. So I'm going to do that when the features numeric, which would be this one right here, this condition. So I'll only calculate skew here, and I'll do it feature. That'll work. That's just fine. Down here, if it's the if the feature's categorical, I'm just going to set skew equal to a dash because I got to put something in there. So let's go ahead and handle this now, inserting this into the row. So let's handle this path right here where we're inserting the row into the data frame. And after missing, I've got to put the skewness score, which is going to go right here. So I'm going to add skew in that spot, and it'll put in either a dash or it'll put in this score. And you know what I better do, since this is the only spot where it might be a number, I better apply my round to right here in this spot. So round 2, only if it actually calculates a skewness score. Otherwise, it'll put the dash in. Next, let's handle the Kendall and Spearman correlations. So I'm just going to, in this case, we're not going to calculate those in the C to N or N to C scenario. But I'll go ahead and do that. Let's see. It will be skew. It will be after the p-value. Where did I put p? Right here. Okay, so I'm just going to add 2 more right there. That'll handle those 2. Next, let's put type and unique. We calculated them up here. They got calculated before the if block, so they'll definitely be available to me right here. So after skew, I'm going to put dtype and unique. All right, so let's add each of these things. We know we're going to need those. I'll save this for last. Let's add them here in the end-to-end condition. So after missing, I'll put in skew. Now at this point, I haven't rounded skew yet right here. So I'm going to copy the version that has the round 2 on it. And I guess I'll just go ahead and do it right here when I'm calculating skewness. So then when I create the variable there, it's already rounded when I put it in right there. Dtype unique. Now I've just got to add Kendall's tau, or the Kendall and Spearman correlations. So not a problem. We're going to calculate those using the SciPy package, and I'm going to call them, I've already written the code somewhere else, so I'm just going to copy and paste this in. I'm going to do it right here after I calculate the linear regression equation. So here's what I've got. I've made tau, rho, that's what it is. It's not po, yeah, anyway. Tau, and then the p-value for tau, rho, and the p-value for rho. Using the stats package we already imported above, Kendall tau, Spearman r, passed in the feature and the label for both. Now they're available, so I'm going to insert them with a round function after, or exactly where they go, so after the r. Right here. You know what? It's time to break this into a couple lines, I think. So I'll bring that here and I'll start, maybe I'll put 1 on this line. Round TAU, round 2, and maybe I'll do this one on the next line. Right here, I'll do round RHO, round 2, comma. Okay. So I've inserted all of my new columns for the end-to-end condition, the C to N, N to C condition. Now here in the C to C, none of these apply. So I just got to go through and, well, sorry, I take that back. Skewness doesn't apply. So I'm going to put 1 here after missing for skewness. But then dtype, I mean, it doesn't hurt to have it here. I don't need it for this. But since I've calculated it, I may as well use it. So I'm just going to add dtype here, unique here. Unique will come in handy for a later cleaning step we'll talk about. And then for Kendall and Spearman correlations, I'm just going to add another couple of dashes right next to where the correlation is. So 2 more right there. All right, let's see if I've got any errors. I'm going to go ahead and run this and use it on the insurance charges data set. There we go. Got one. Let's go ahead and take a look. Dtype. It's a property and not a method. I want you to recognize this error and get used to it, so I'm going to leave this error here in the video. Because it's a property, I don't need the parentheses after it. So let's go up to where we calculate that. Type, dtype, right there. Take those off. We don't have that anywhere else. It should apply through to everything else. All right, here we go. So we still have our visualizations being created like we did before. Now I've got the missing percent here, the skewness of the feature, and I can see here that none of them violate the -1 to 1 rule, but some people go back a -0.5 to +0.5 rule. So I mean, it depends on what rule you want to apply. This one, you could potentially say children is too skewed. However, children is also discrete and not normally distributed. I mean, it's somewhat normal. Basically, it's kind of borderline. You might be able to say that the Spearman's a better measure of correlation than R is. But either way, I've got all of them here, and I can kind of calibrate myself against all of these. All right, let's try it with the NBA data. So this one has a lot more visualizations, and it's going to take a little bit more time, but that's okay. We'll get that one running and started. So here in the images, notice where we have a scatter plot, we're still showing just the regular Pearson correlation. If you want to, you could modify our scatter plot function that we made in the prior video and include the Kendall and the Spearman here as well, along with maybe skewness and unique and those other metrics, just to help give that same information available on each of these, but I'm not going to worry about that for this video. So let's scroll through here, see if we've got the table yet. All right, here's what we got. So let's identify some skewness that's out of bounds. So blocks, yes, very positively skewed. That tells me that this Kendall tau, this is a much more accurate correlation than this one will be, but you can see they're very close to each other. The p-value, the one we kept here, is the p based on the original Pearson. So one way you can modify our code is you could add some decision criterion in there and maybe only show the p-value of the one that you think is most appropriate. For example, if skewness is outside -1 to 1, show the p-value for tau. If it's an integer instead of a float, and if there aren't a whole lot of unique values, like in this case, game started, 79 is a lot of unique values. Do you hopefully understand what I mean by even if it's discrete, if you have a whole lot of unique values, it can start to feel more like a smooth, continuous feature. There's not a hard and fast rule on exactly when we should treat it as, well, I mean, there are some suggestions, but not like general consensus agreement on when you would absolutely call this something, fully discrete or fully continuous. There's technical definitions, but I like to have both of these things here to help me make some judgment calls. Age, I mean, it's measured discrete in this data set. There's only 22 values. You could potentially argue that, well, I think 22 is even still too many. Personally, what I'll often do is I'll say, okay, if there's fewer than 10 or 12 values and it's discrete, I might prefer something like the row over the correlation, but that's definitely not something that everybody goes by. Everyone kind of has their own opinion on that. But this is much more helpful, these extra measures in this data set where I've got so many that violate skewness. Not as many. I still don't have any true rank ordered features where I'd say I'd obviously have to use the Spearman correlation. Let's try the airline satisfaction. See what we get now. Okay, these are mostly, because our label here is satisfaction, we're not going to have any need for these other correlation measures anyway. And that's okay. That's just, because we've chosen satisfaction in this data set as what it is, as our label, as the thing we want to predict. And so it's not really going to come up. However, we did add those metrics for all feature types, which means that we'll still have the ability to get the number of unique values, the data types, and the skewness if it's a numeric feature. So let's see if we've made it through all these yet. Not quite. Here we go. So you can see we still get skewness, and it still is calculated for each of these. Oh, but this is a good example of where I would say that these ratings, these are Likert type scales. Strongly disagree to strongly agree, and there's only 5 options or 6 options. This is a good example of where if I was predicting something that's numeric, I would very much prefer the Spearman correlation over the Pearson correlation. This definitely qualifies as much more of a rank ordered type of data set. In fact, why don't we switch and predict something other than satisfaction so that applies. Let's see if we can predict. I'm curious if departure or arrival delay has any weird correlation with anything else. Let's use this one as our label and call this one more time. It's still going to take a moment to go through and create the visualizations for us. I'll just pause it. Actually, this is kind of interesting. I want to share some of these as it's going through. So arrival delay in minutes on whether they're satisfied or dissatisfied. Big shocker here. Dissatisfied customers experience arrival delay at a much higher rate than those who are satisfied. But this one was interesting. Although I guess the difference is not quite statistically significant. Disloyal customers have more arrival delays. That makes sense. They don't come back and repeat purchase again if they get a lot of delays. Let's see here. There should be no effect. Well, actually, but there is interesting. Arrival delays by where they sit. So business class tend to have fewer arrival delays. That doesn't make sense. They all sit in the same plane. What we're seeing here is that the people who get an arrival delay are less, and are okay with it and keep going back to that airline, are less likely to pay for business class. So maybe that tells more about the type of customers who they have. All right, let's see what else we got here. Flight distance, positively correlated with arrival delay. No surprise there. The longer the flight is, the greater the chance there is for a delay. Seat comfort, this is negative. So this is interesting. The more there's a delay, the less comfortable they perceive their seat as being. That's that negative. That's how we interpret that. So when people are complaining about seat comfort, well, I guess that makes sense. If you're on the plane longer, seat comfort is going to make more of a difference. But sometimes people will complain about something else when they really mean. Okay, here's an example. Another significant negative relationship. They're complaining about the food and drink the more their flight gets delayed. So is the delay really making their food and drink worse? No, they just got upset because they're delayed and they're looking for things to be upset about, like the food and drink. Really common with customer satisfaction surveys. But once again, like I mentioned before, because these are all clearly rank ordered data, each of these ratings-based features, gate location, in-flight Wi-Fi service, rather than use a Pearson correlation R here, I would modify or suggest that you modify our scatter plot chart to be much like the changes we just made to also include Kendall and Spearman. Maybe include, I really don't need data type and number of unique values since I can see that right here. But you could add each of those, percent missing data, data type, number of unique values, any of those things we included, skewness, as other metrics to put right here, so that we have them as we're looking through each of the charts. Okay, I decided to stop talking about it and actually go ahead and modify my scatter plot chart in the same way we just modified the bivariate function. So you might remember this chart from the prior video. What I did was I simply added the same calculations for Kendall's tau and Spearman rho, and then I added a skewness score for both the feature and the label. Calculated those right under here. So you already had this if you're following along with the last video. I added these 4 lines. And then I modified these right here to include the p-value for each one and then the skewness at the bottom. So now when I print out my scatter plots, I get regression equation just like I did before, the Pearson correlation and p-value, Kendall, Spearman. And so I can look at this. I don't know how important it was to add the skew, just kind of personal preference, but I can look at this and tell, all right, this is clearly even though it's a discrete feature where age comes in a whole number, it looks pretty continuous because there's so many possible numbers here. I can see that there's probably some sort of skewness issue here with age because I've got so much data down here and so little up here, but I went ahead and included it anyway. So I've got everything I need to know that I'm probably looking at the best score for me to use is this Kendall's tau, because I don't have a normal distribution for charges, yet it's also not rank ordered data. So I'm not going to do the rho or the R. I'm going to use the tau right here, and that's my best metric for this. So I went ahead and we were running this back here on our airline data as well. I'm getting all the same things down here now too that I can use. What's interesting is look at some of these down here in the flight data where we have we switched over to arrival delay in minutes, and we're looking at that as our label, and we're looking at their subjective rating of things like seat comfort. Because we have this rank ordered data here, some of them I noticed right here, the correlation for convenient departure arrival time. If we had just used the Pearson correlation, that has an insignificant p-value. But by including these, you can see that when using a more appropriate one, like the Spearman row, it's not a whole lot. First of all, it's actually negative rather than positive, which is very interesting. That by taking that into account, it changes the sign completely, meaning that as the convenience goes up, the delay seems to go down. It's probably the reverse actually of it. This is actually the Y. As their delay goes down, their perception of the convenience goes up. So this was giving us wrong information anyway. And that's why it's useful to have all three of these metrics, as well as information that helps you make a decision about which one of them is most appropriate. All right. It's still running, printing out a few of these charts. I'm not going to go any further though and show the table. I think this is good enough now to make the point.